All right. Time to begin the fun. This is CSC 1351. If you didn't know where you were, here is our schedule. Today is, the board is not on. Yes, the board is not on. I have to plug that in. It won't work if I don't plug it in. All right, so the board is on. Today is February 19th. We're going to start time complexity searching and sorting. Yay. Before I get into that, I guess you probably want to talk about the quiz, right? Okay. All right. Let's take a look. Okay, so we have this this class called Capybara here. Now, as I've told you, whenever you get these kinds of problems, what you should do right after the quiz is over, you should go to your home computers and you should plug the code in and you should run it, right? There's nothing that is going to do more for you than running code and experimenting with it yourself. And just a reminder, if you're feeling overwhelmed and you're lost, okay, this is a very bad place to be at this point in the course, but if by some chance that's where you are, just find one thing that you can figure out, okay? Just make one little bit of progress against the dark. It may not get you past the course, but it might get you on the ways to understanding the material and maybe passing it next time. I don't know. All right. So what the Capybara class does, we have to take it one step at a time, like we do any code. So we're going to start with main. We're going to printf the result. So that's going to be a string. That's going to be a new line. We're going to call the bark function with 5. So I call the bark function with 5, and that goes to this line here, right? Where it calls the bark function helper function with 5, 5. So this comes here with 5, 5. Is it less than 3? No. So then we put a parentheses and we call it with 6, 4, right? And then we enter the function again. So this time it's 6 and 4. And is 4 less than 3? No. So we call it again. Shoot, I don't have anything to write with. So we call it with 6, 4. We have one parentheses, we call it with 6, 4. We call it again, we get 7, 3. Is 7, 3 less than 3? No. So we get another set of parentheses and we call it again. And this time we have 2 and 2 is less than 3. So we return the 2 and we have the 2 parentheses outside it, right? You can just sort of follow it step by step and make little annotations on paper to help you keep track. But if you just sort of follow, what you need to do is you need to execute the code line by line in your head, right? Everybody okay? Anybody have a question? All right. Fibonacci. So I corrected this one. It was pointed out to me that that there was a typo. That was a 2. So I just changed it to an N now. So your papers have something different. But the thing that I showed you for Fibonacci, right, is you're adding the previous 2 numbers in the sequence. And that's what this line does, right? It adds the n-1 and the n-2. Technically, Fibonacci's are supposed to start with 0, 1, 1, and I messed that up, but that shouldn't affect your answer here, which is to figure out what the next 2 are going to be in terms of that. Any questions there? All right. Which of these is the correct example of an anonymous inner class? So here you have to use your eyes. So one of the things that you need to do to be a computer scientist, to be a programmer, is you need to be detail oriented. You need to be able to look for and pick out the little details that make one thing different from another. And just doing this with a program that you're trying to debug is super hard. But if you've got something like this, right, and each variant is there right next to each other, and you can just sort of go character by character, it may still be challenging, but it is easier than what you would face in real life, right? So this is just to help you try to focus on details. So here we have runnable R equals new runnable, public void run, system.out.println, and then the close parentheses. This one looks to be correct, right? I think I put the correct one first in my version. Let's look at the next one. I left off the parentheses, right? This one also leaves off the parentheses. This one introduces keyword protected. It's got to be public, right? Because runnable is an interface, and the void run is a public method. It can't be protected here. It has to be public. And likewise, this one is missing the public keyword. And this one is even worse. It's missing the whole method declaration. It doesn't have a public void run on it at all. So those were your choices, and that was how you identify the correct one. Any questions? All right. All right, and that's it. That's all there was on the quiz. All right. So let's take a look at what we've got going today. Sorting, searching, and big O. Okay, so what we're going to do is we're going to look at a sorter, a generic sorter, and then some sorting examples. And then, so let's start with that. Let's take a look at the sorter. So sorter is an abstract class. I don't use these very often, but I did in this case. And it's got a couple of different static methods. It's got a static method to create an array. It's got a static method to duplicate an array. It's got a static method to compare two arrays. It's got some other things to check out validity of sorting. It's got, oh yes, it's got a check method, right? And to check to see if something is sorted. It's got a swap method. So the swap method is kind of important. What the swap method does is it takes an array and it takes two positions in the array and it swaps the contents of those two positions. So the way it does it, right, is it takes what is at array I and puts it in a temporary variable. Then it overwrites array I with what's in array J, and then it overwrites what's in array J with what's in the temporary variable. Cool. We've got a print method for the array. Got two variations, one that takes a start and an end and one that doesn't. We've got the abstract sort method. So I'm going to have a couple of different methods of sorting, and I'm going to overload this sort method to do it in different ways. And then let's see, a little usage message just to be a nice programmer. And then I have a main method, which is going to do some stuff which I'm not going to teach you how to do, right? It's called reflection. But the way the program is going to work, I'm going to say Java sorter, and then I'm going to give the sorting algorithm that I want to use. And then it's going to run it a bunch of times and do timing tests and correctness tests on it for me. So a lot of cool boilerplate stuff like that. Any questions? Michael? Bo. Okay, Bo.
What's the difference between an abstract class and just a normal class?
So an abstract class is kind of in between. I mentioned it briefly in the beginning. It's in between an interface and a regular class. It's got some methods that aren't implemented and some that are. And the keyword abstract is put on the class itself and on the methods that aren't implemented. Another question, Danik? Content above the print method. I'm sorry, which two? Swap? Oh yeah, so the swap is we're gonna take an array and we're gonna take two positions within the array and we're gonna swap the contents of those two positions in the array. So what I'm going to do is I'm going to get out I'm going to get what's at array I and put it in a temporary variable. Then I'm going to overwrite I with what's in J. And then I'm going to overwrite J with what's in the temporary variable. And that should swap the two. All right, let's take a look at the slide again. So the first sorter we're going to talk about is the bubble sorter. And the bubble sorter has the distinction of having been mentioned by a US president. Am I getting sound? Where's my sound? I'm not getting sound. This is terrible. I'm not sure what to do about this. Everything looks like it's working. Well, you can go look at the link later, I guess. But it's.
Would be the wrong way to go.
Come on.
There we go. All right. So the content, you can watch that later. The content there.
Computer science.
We've got our slides.
He was, this was before he was elected, and he was doing an interview at Google, and they thought it would be funny to ask him some Google entrance questions, and he was asked about sorting. And he said, I don't know what you want to do. It's just, but bubble sort might not be the way to go. Well, we're going to start with bubble sort anyway. And you can, now all the sorting routines are available to you online in videos as interpreted by Dance. Yes. So we're going to see the bubble sort dance. I just love these.
My right ear will be very happy.
They're not moving. Why are they not moving?
This is hard.
Oh, okay. Yeah. Yeah. All right.
Oh, yeah.
So they all pretty much start out the same way. Okay, now we get our array. Shuffle it up. There it is. There's our array. There are the indexes for the array and the values. Now you see what they did is the first two elements of the array came out and they danced together. And every time they dance together, the one that's the smaller is going to go down, right? So if they're already in the correct order, they'll come back to their same places. So they're just going to go down the whole array, comparing to each other, and then either swapping or not. Now this dance, as I say, this dance, there are a bunch of different sorting algorithms, and this dance troupe has done them all, but we're not going to watch them all. I mean, you can do it on your own, of course. Oh yeah, they have all the sorting algorithms are done with dance, right? Okay, all right, that's probably enough of that for now. All right. So bubble sorter. Let's take a look at the algorithm. Okay, so it's pretty simple. I mean, the idea, of course, is sorting, right? Is we want everything to be in ascending order in the array. And what we're going to do in this one, now I have a Boolean done flag that tells me if I'm done sorting. I have a passes flag. This is just for diagnostics. If I just want to figure out how many times I've gone through the array, I don't need this at all, but it's just there for figuring something out. So I'm going to have while not done. So I initialize done to false. While not done, I'm going to increment passes. I'm going to set done to true. And then I'm going to go through the whole array. I'm going to start with 1, though, not with 0. I'm going to start with 1 and go through the length of the array. And I'm going to say if array at I minus 1 is greater than array I, then swap array I minus 1 and I and set done to false. Okay. So what I'm doing is what those dancers did, right? I'm taking each pair of elements in the array, I'm comparing them, and if they're out of order, I'm swapping them. Okay. And if I swap something, I'm going to set the done flag to false because if I'm only done if I can get through the whole array without swapping anything. And in general, I'm going to have to go through the array about n times because the worst case scenario is I've got the smallest element at the far end of the array, and it takes me n times to walk it all the way back, n times through the whole array to walk it all the way back to the front. So this is going to work, but it's going to take a while. So let's, you know what? I didn't remember my benchmarks for this. So I'm going to do some guessing. Let me put minus EA, and I'll put say an array of 100. 10 times, I think is the way this works. All right, so that's not big enough for me to notice. Let's do 1,000. Okay, now we can start to see the times, 10,000, 10 times. Let's put it 100 times. Okay, so what I'm doing, right, is I'm taking this bubble sorter routine, I'm taking an array of size 10,000, and I'm filling it with random numbers and sorting it, and I'm doing that 100 times. And I'm measuring the time it takes, and then I'm computing the average and the standard deviation of that time. So you can see how long it takes to sort 10,000 arrays 100 times. Well, how long it takes to sort 10,000 integers on my computer using bubble sort is 0.147 seconds. Cool, right? All right. Let me change that number just to see something. Let's say I'm going to go back to, let's say 20, and I'm going to move this to 20 to 2. So it's 20,000. I'm going to say twice as many things to sort. And how long is it going to take? The crowd waits. How long do you think it's going to take? Okay, there it is, 0.642, right? So let's see if I were to just compute that. That's a little more than 4 times longer to sort twice as many things. All right, let's just keep that in mind. All right, our next candidate. Oh, this is probably what I should have done, huh? 3,100. Let's do that one. I don't know why I didn't think of doing that one. 3,000. Oh, that's super short. Okay. Well, anyway, yes.
Is there a reason why it's sort of at 9 equals 1 and not 9?
Yes. The reason is because I'm comparing two things, right? So Kyle asked why I started at 1 and not at 0. And the reason is because I'm doing this I minus 1. That would go badly if I used a 0. Okay. Yes. Shoot, Isaac? I didn't. We're getting to time complexity. I haven't introduced that subject. I'm going to introduce that in these lectures, but I haven't gotten to that yet. All right. Selection sorter. So this is another simple sorter, right? And so I have a little graphical depiction here. The idea is what we're going to do is we're going to go through the array and we're going to look for the minimum element. And we're going to swap that with, you know, wherever it is and take that minimum element and put it in first. And then we're going to take the rest of the array from 1 on. And we're going to find the minimum element and we're going to put that in position 1. And then we're going to take the rest of the array from position 2, find the minimum element and put it in position 2. Makes sense, right? Fairly straightforward. So in this case, we're going to say I equals 0, I plus 1 is less than array.length, I plus plus. We're going to set I min equal to I. So I min is we're going to keep our track of what our minimum is. We're going to say int b equals I plus 1, b is less than array.length, b plus plus. And then if array at b is less than array at I min, I'm going to switch I min with b. So what I'm storing in I min is not actually the value, the minimum value. It's the index of the minimum value. All right. So when at the end of that, at the end of this loop here, I can swap with the I min with I, and that carries out my selection sort. Does that make sense? Does anybody have a question? Yes, Drew. Well, that's when you set it to I here, that is the initial value, right? Each time through this loop, we initialize it with I. So the first time through the loop, we initialize it with 0. The next time through, we initialize it with 1. The next time we initialize it with 2, and so on. Okay, because we want the minimum value of the remainder of the array to go in that slot. Any other questions? Yes, Vanek. I'm sorry, what?
Can you explain why you chose I plus 1 as a condition?
Oh, instead of I less than array.length? Because in my next loop, I'm going to start with the next position, right? And I think nothing would break if I left off the +1, but on the other hand, nothing would happen either in that last one because the following loop would be 0 length. Any other questions? All right, good. So that's my selection sorter. And let's see how it does against my bubble sorter. So we're going to go for 20,020. Is it going to be faster or is it going to be slower? It looks like it's faster by a good bit. Let's see what happens when I bump it down to 10,000. Okay, so you see that it's a comparable thing. It's something around a factor of 4 once again, right? It's to bump the array size by a factor of 2, I get a factor of 4 slowdown, right? Good. Oh, yes, I didn't actually run it. And look, I got a different time, even though it's this. No, I didn't get the different time. I got a very similar time. Let's pretend I know what I'm doing. All right, so there's the selection sorter at 10,000. And there's the selection sorter at 20,000. Okay, so it's about 4, and you can see 3 times 4 is 12. But it is significantly faster than our bubble sorter. At least, you know, this test, what I've done. Okay. All right, sorry about that. Any questions? All right. Next slide. Okay, so the question is, can we do better than these 2 functions and these 2 sort algorithms? And the next 2 are going to be the merge sorter and the quick sorter. Now, the merge sorter, well, it is going to be faster. I'll spoiler alert there. But the way this works imagine that I'm sorting a deck of cards, right? And I have, I don't know, I figure some order for the suits. There's probably some standard order. I don't know what it is, something like heart, diamond, club, spade, or something like that. And then so you have you have sort by the number value, and if the number value disagrees, you sort by the suit, right? Okay, and then you sort a deck of cards. So you're given a deck of cards that are all out of order. Now, the way you sort them, the way you could sort them, is you divide them into two piles, and then you sort each pile, right? And the way you continue doing that, you continue dividing it into two piles and sorting each pile until you've got two cards, right? And you know how to sort two cards. You just look at them, you put whatever one is first, right? And now what you have to do is you've got two sorted piles, and you want to combine them into one sorted pile. So what you do is you look at the two face-up cards. You put the cards face down, you pull the card off the top, the other card off the top, whichever one is smaller, you put that face up, right? And then you pick up the other side, and you keep doing that, right? You merge them together, one card, by looking at pairs of cards at a time until you get the whole deck sorted, right? So the way that looks, it's a little more code. First thing I'm going to do is I'm going to compute the midpoint of the two so I have an array that I'm going to sort, right, from the start position to the end position. I'm going to take a segment of that array and sort it. And what I'm going to do first is I'm going to find the midpoint, because I want to divide this deck into two. And one way to do that would be to say start plus end over 2, right? But that method actually is vulnerable to round off error if I have a very large array I wish to sort. I can say start plus end, and that can overflow the integer allowed values for very large arrays. And then everything just doesn't work. So the trick is you compute the midpoint this way. You say start plus parentheses end minus start, close parentheses over 2. Right? That prevents you from ever adding two huge numbers together. Instead, you're subtracting two huge numbers. And so you don't run into the same overflow error. But you could just as easily say start plus end over 2. Now, the Java framework, when it was originally published, made available, the sort routines that were built in were vulnerable to this bug. They had the integer overflow problem, and they later corrected it. But it's kind of an interesting problem. Sometimes when you make your problems bigger, you find interesting new problems. Okay, so now what I'm going to do is I'm going to create two arrays called first and second, and I'm going to make them each big enough to hold their respective piles. And what I'm going to do is I'm going to go through this first array, and I'm going to copy into each element. I'm going to copy from the array I plus start, right? And then I'm going to do the same thing with the second array, but I'm going to copy from I plus mid. So I'm copying the array into two smaller arrays, right? That's me cutting the deck into two, right? You with me? Cut the deck into two here. All right, now, oh, I'm sorry. I glossed over a step, right? What I did is first after I figured out the midpoint, then I called sort recursively, right? I called sort recursively on the subarrays, right? So I've called the sort however many times all the way down recursively. I skipped over that. Then after I've done that, I'm going to make the two decks, right? The first and the second deck. Now those decks, remember how we described it. Those decks should already be sorted at this point, right? So now what I have to do is merge them. And the way I'm going to merge them is I'm going to pick these two integers, I1 and I2, for indexing into the first and the second array. And then I'm going to have this other integer I, which I'm going to set to start. And I'm going to fill my original array back in. So I'm going to sort in place in the array. And so what I'm going to do is I'm going to say, if the first I is less than or equal to the second I, then in array I, I'm going to put first I1. And then I'm going to increment these two indexes that I used. And if that's not the case, then I'm pulling from the second array and I'll index the second and the I++. And this loop only runs while I have, while I1 and I2 are less than both first and second. Well, they're both still in range. And then if I get past the end of this loop, then only one of those two decks still has cards in it. So I just copy whatever remains in the first deck and whatever remains in the second deck into the array. That's how I merge. It's a little bit more work than the bubble sort, right? Yes, Ty. Yes. This uses more memory. It can use, you know, depending on whether you want to pay the memory cost, you can or not. So in computer science, there are almost never right answers. There's almost never a situation where this is the way to do something. There's usually 5 or 6 different ways with different trade-offs between them, and you have to pick. All right. So one of the things with merge sort is it uses more memory. All right. So let's take a look. Anybody have questions on how merge sort works? Yes. Name? Cat.
Can you scroll up?
Yes, I can scroll up.
So what would happen when you're like initializing and like was off?
Well, it's so the way integers work in Java is it rounds down.
So what is that?
Yeah. So it can be that the two piles aren't exactly the same length. We try to divide them into two equal length piles, but if you have 5, then one pile is going to be 2, one pile is going to be 3. That's just the way it is. But we can handle that with our merge sort, with our merging algorithm, right? Because what we do, right, is we have this stuff at the end to pick up whichever pile has cards in it that didn't get merged. Okay. So let's see how fast it is. It's a lot faster, isn't it? I mean, the bubble sorter, I mean, the selection sorter did that in 0.12. This is 0.05, right? I'm sorry, 0.005. Let's make it twice as big. I made it twice as big. It took twice as long. Roughly. Okay. So, so this gets us to the concept of time complexity. This is a concept that computer scientists came up with to describe how things get bigger, how things behave when they get bigger. So we're going to find out that bubble sort is order n squared. So every time I double it, that's going to take 4 times longer. And we're going to find out that merge sort is order n log n. And n log n means that, you know, for a lot of the small numbers, it's going to look almost linear, but it's a little more than linear, right? It's a little more than n. Log n, it grows pretty slowly, but it is still growing. So how do we get those numbers? How do we come up with selection sort and bubble sort are going to take n squared, and this merge sort is going to take n log n time? How do we figure that out? So let's go back to our bubble sorter. Now, I told you that the longest number of the biggest number of times we can go through this while loop with this not done. The biggest number of times we're going to go through there is going to be n, right? That's if the smallest number is all the way at the far end of the array. Probably on average for a random array, the minimum value might be in the middle. Anyway, it's going to be, let's call it n over 2 times on average that we go through that this while loop goes, right? And that while loop goes over the whole array. So that's n times. So we have a loop. So you have n2 times n comparisons that we're doing. So that's n squared over 2. We'll just say that grows as n squared, right? We're not worrying about the factor up front, whether it's a 1/2 or a 3/4 or whatever. So that's going to grow with n squared. So if I double it, it's going to take 4 times as longer. To make it 4 times bigger, it's going to take 16 times as long, right? That's the behavior of that bubble sort, and you can get that by looking at that code, right? You can see that because it is a nested array. All right, and the same thing is going to happen with a selection sorter. With a selection sorter, each time I'm finding the minimum. So I'm going to go through the array n times, then n minus 1 times, then n minus 2 times, and so on. But if I take a sum that goes like that, it's going to wind up being n squared, right? So if you want to think of it this way, the average length of this array, well, this array is always going to be n minus 1, and this is going to be on average n minus 2. So again, we're n squared, right? So both bubble sorter and selection sorter are order n squared algorithms. Now, what's going on with merge sorter? How do we know that it's n log n? That seems like a pretty tricky thing. So first, I'm going to write the time complexity for this algorithm in a math form, and then I'm going to show it to you in a graphical form, which hopefully will make more sense. So in the math form, we say the time it takes for this merge sorter to sort n things is going to be twice the time it takes to sort half the number of things, plus some constant times the size of the array. Okay, and so that math, what that math is saying, right, is I'm going to say each of these is half the size of the array. So 2 times n over the time to sort n over 2. That's what where the recursion comes in. And then this next part, we're going over the array, say 1, 2, at least 2 times, right? So it's something like we're going over each element in our subarray twice. All right, so that's how we map that math expression onto our code. And this particular math expression and this particular, n equal 2 times n over 2 plus kn, that's going to show up a lot of times in your computer science career. Just FYI. Expect to see that a lot if you stay with the program. Okay, let's look at the sorting of things graphically. Okay, so let's say first I'm going to sort 4 things. If I sort 4 things, I start out with that array, then I sort these 2 arrays, right? And then I sort, well, these smaller arrays, which are just one thing, right? So I have 4 by 3. And then if I sort 8 things, first I have this whole array, which everything in it. And then I have the subarrays, and then the subarrays of that, and so on. And so this time I had 4 by 3, this time I have 8 by 4. And now I have 16 things, and it's going to be 16 by 5. And you see what's happening is the amount of work I'm doing is going to be proportional to this picture I'm drawing, right? And this picture that I'm drawing is going to be n things across, but it's going to be log things long, right? So the amount of work that I'm actually doing is this times this. This, and 4 times 3, 8 times 4, 16 times 5. So that's n times log n. Does that make sense? At least a little bit? Somebody have a question? Okay, so that's a picture that you can have in your mind of how n log n maps to this type of equation that I've got up here. All right, and so that is because of that math trick and the way it maps to code, that's why the merge sorter is so much faster than a bubble sorter or a selection sorter. So a bubble sorter is going to, I've sorted 20,000 things and we had to wait a while, right? And if I doubled that, a few more times, it would just be unthinkable to sit here and wait for it to go. But if I go to this merge sorter thing and I even add a 10 on here, right? I barely waited, right? Because as it gets bigger, it's more efficient. So that's the key to that. Any questions on that? Okay, let's take a little digression here into big O notation, then we'll come back to the quick sorter. So the way we're going to do big O notation is the big O means it takes order n time. It's linear, right? That could be 2n, it could be 3n plus 1. The idea is I want the asymptotic behavior. I want the behavior of the function when it gets very large, and I don't care about the constants out front. So if I ask you what is the big O behavior of 3 times n plus 1, the answer is on, right? Now, saying order 2n is always wrong, right? If I ever give you something and say, is the answer order 2n? The answer is no, because order 2n is wrong. You can only say order n. You want to discard that constant out front. Order n plus 1 is wrong, right? Because that's not the asymptotic behavior, right? That plus 1 is not important. Okay, so technically, big O is an upper bound, but we will always think of it as a tight upper bound. We're always going to say that's the behavior of the function. And you can get into more details about these things in later computer science courses. We're still an intro course here. Yay. So technically, the big O for quick sort is order n squared because of a worst case analysis. But in this course, we're always just going to call it n log n, and we'll talk about why in just a minute. Anyway, big O notation is an important concept for computer science. You're going to hear it again and again and again. It's kind of your bread and butter if you're a computer scientist. So you need to wrap your heads around this basic information here. All right, let's go back. Any questions on this? Yes, Ding.
Yes, sir. On the quiz test, so basically just using more O to N or O N.
Yeah, if you see O2n, you know it's wrong.
Would O N to the power of 2 be something we ignore?
No, n squared is bubble sort, right? That is an asymptotic behavior. N cubed is also it's just the plus. So here's the other thing, right? Let's think about it this way. If I say n squared plus n, what's the asymptotic behavior of that? It's n squared. The n is going to be unimportant when n gets very large. If I say, what is the big O for a function that takes 5n plus 100 log n, the big O notation is n, right? Because for very large n, that log n is just not going to matter. It's going to be too small. All right. So let's look at quick sorter 2. I had a quick sorter that I wrote before, but I decided it wasn't good enough, so I went on to 2. And this is a quick sorter works kind of the reverse way of a merge sorter. So a quick sorter is kind of a cool algorithm because it relies on a random number. So what you do is you pick a random index in the array, and that whatever value is at that index is your pivot, and you're going to sort the array into things that are less than the pivot, things that are equal to the pivot, and things that are greater than the pivot, right? And then you're going to recursively call quicksort on the things that are less than and on things that are greater than the pivot. So in merge sort, we did a recursive call, and then we did some linear work. Here we're going to do some linear work, and then we're going to do a recursive call. So it's kind of doing things in the reverse order. So let's see how that looks. So I take my random number generator, which I have as a public final static. Oh, it's on the class sorter. So it's from the base class. So I have public final static random rand. Okay, I'm going to say next int, I'm going to say n, where n is equal to n minus start. Let me back up. First, I'm going to calculate n, which is n minus start. And I'm low on power. Hold on. am I doing that time? Oh, I got 4 whole minutes. All right. So first I'm gonna come up with n, which is the difference between my end and my start. Now, if n is less than 2, I've got 1 or 0 elements in my array. It's already sorted, so I don't have to do anything. Next, I'm going to find my pivot, which is going to be a random position between start and end. So random n is going to be 0 to the value end minus start, and then we're going to add start onto that. So that will give me a random value between start and end. The pivot value is going to be whatever is at that pivot. Now I'm going to partition my array twice. That is, I'm going to move all the elements that are smaller than my pivot value to the beginning of the array. And next, and then after I do that, I'm going to pivot with, I'm going to partition again with pivot plus 1. So I'm going to have my array chopped, shifted into 3 parts: less than the pivot value, equal to the pivot value, greater than the pivot value. Make sense? All right, and then after I've done that, I'm going to sort from the beginning of the array to the end of the less than, and then I'm going to sort from the beginning of the greater than until the end of the array. And then here is how I'm going to do the partition, right? So what I'm going to say is I'm going to have an I1 and an I2. I'm going to have one at the start and one at the end. And while the start is less than the end, I'm going to say if array I1 is less than the pivot value, then I just increase it. So I want to have all the low values lower than the pivot value at the start of the array. So I'm just going to start at the beginning of the array, and while it's already lower, I'm just going to keep moving that in. And then I'm going to do the same thing at the end, right? I'm going to say while I2 minus 1 is greater than or equal to the pivot value, then I'm just going to shrink that in. So if everything is already in order, I just move the array indices in, right? And then if I've gone through both of those and both of those things fail, that means the 2 things are out of order, right? We have something here that's greater than the pivot value and something here that's less. So if that happens, then I'm going to swap them. All right. And then I shouldn't ever get to this statement because this should be an exhaustive case, right? And if I do that, and if I march those things in until it gets together, then I have my array partitioned. Make sense? Anybody have a question? Okay, that's the basics of how the selection sorter works. We'll delve deeper into its mysteries next time. Tune in for sorting adventures in the next dimension.